Alrighty, folks. Good morning. Today we are sort of continuing our conversation about plate tectonics. Some could say even possibly wrapping it up, since we already talked about volcanoes, with the conversation about earthquakes. I'd like you to take a moment just to appreciate how much time it took me to italicize every other letter on that word to make it look like it's caught mid-shake. Isn't that awesome? High-tech stuff here, nothing but the best for you guys. But I think I might even had to put some spaces in there a little bit. So earthquakes. Any of you guys ever been in an earthquake? Felt an earthquake? Felt is more appropriate around here. Been in is, kind of what you see on TV or a movie, and it's really bad. Around here, every so often, you'll feel some rumbles or shakes. Northern New York, up along Messina, Watertown, they're along the border. They get some every so often. Albany area will get some. There was one in Rome. We'll talk about that on the appropriate slide, I guess. But point being, we don't get a whole lot of earthquakes around here, but you've seen them on TV. So what is an earthquake? Well, it's just that. It's when the earth quakes, right? Sudden trembling of the earth caused by the release of accumulated energy in rocks. And that's really what we're going to talk about a lot, is the energy. We call this seismic energy. Whenever you see the word or the prefix, I should say, size, it's a good $5 bet that you're going to be talking about something earthquake. Seismologist, seismograph, seismogram, seismic energy, seismic. Okay? In fact, I have a question that floats around. I think it made the transition over to D2L. It's one of those, the seismologist interprets the seismogram that was made by the seismograph and measured seismic energy or something like that. And then there's 4 iterations of it. Okay. So make sure it starts with seismologist when you pick the one. That's the person who, ologist is always someone who does something, right? So make sure if we see that question this semester that you grab the right one there. There's a couple ways for seismic energy to be released. Again, it needs to be pent up. It needs to be stored. And we could store that energy from plate movement. We talked the other day how North America and the Pacific plate, the North American plate and the Pacific plate, are moving in different directions. And of course, they are side by side along each other. And the hardest part here, and this is even for me to believe, I wouldn't point it out otherwise, is that after all these years, it's not worn smooth. If you've ever walked down the hallway, we've got these lovely brick walls here. You either dragged your pencil or dragged your finger, and you go, it kind of bumps along as you're driving. I'm sorry, as you're walking. I was also thinking of the rumble strips when you're driving. It's rougher than that. Rough enough that it can get caught up. Kind of like if you've ever locked your knuckles together from both of your hands. And as one plate is moving, the other plate is moving again. Even if they're moving, in exactly opposite directions, it's still it can get caught up. And the question is how much energy can it hold before it pops? All right, and there's some factors that go into that. We'll talk about it. That's your standard way we get earthquakes. Talked about the Ring of Fire, nearly 3/4 of the world's earthquakes and volcanoes. Remember that? Those are all plate boundaries. So plate tectonics, the big one. Around here, as we said, we don't really have a plate boundary, thank goodness. But we still, as I said in the introduction, we still have some earthquake activity here and there. That's from settling. Okay? The Earth is old, she's cracked, and you know what? There were other plate boundaries, before the ones we currently have. Maybe you have a buried one of those. They'll talk about faults a lot. A fault is just a break in the rock. Andy Warhol said everyone gets 15 minutes of fame. I had my 15 seconds of fame back when there was one that was felt in Rome. And the local radio station, I think it was IBX at the time, probably still is IBX, called and talked to me. And somewhere I've got the wave file of that one. That's how long ago it was. And I said, the Earth is like an old house. Sometimes she just settles, and you hear that creak in the middle of the night, and and that is what happens. But it sounded kind of silly on the radio. But at any rate, so that's what settling means. And sometimes settling can be a big shift. There is something called the New Madrid Fault that's down, I want to say in Missouri, and it runs all the way up through Ohio. Big old crack. And when that went in, I don't remember the date, over 100 years ago, it was huge. It was huge. A lot of damage. So, but typically, it's not a big deal when something like that goes. So, as such, earthquakes can really occur anywhere. We have the standard plate boundaries. Well, where do you have plate boundaries? Again, pretty much anywhere. We don't have one in the middle of our continent, but some do. Definitely in the ocean. Ring of fire, we talked about that. And then faults, you hear the word stable continental interior. Stable continental interior is basically what you're living on, okay? There's no faults, or yeah, sure, there may be a little settling here or there periodically, but otherwise, there's really nothing tectonic going on other than you're going along for the ride. We talked about the plates moving 3 to whatever centimeters a year, okay? You are going along for that ride. Slower than a turtle, but it's happening. Just a reminder where your plate boundaries are. Reminder where the ring of fire is. Not sure why they decided to leave Antarctica off of here. They did label the Antarctic plate, but surely some of it would be peeking out the bottom there. So as you see, a lot of the plate boundaries really are out in the oceans or the middle of nowhere, so to speak. And as such, a lot of that kind of stuff doesn't really end up bothering anyone. It doesn't make the news. My online classes, the geology and the earth science, they have a task, a lab that runs the entire semester. And that task is, it's called the Natural Disasters Map. I wish I could have a slightly less horrible name for it. But their job is to keep track of, all the earthquakes, volcanoes, tsunamis, snowstorms, hurricanes, whatever takes place during that semester. And I always warn them. I say, don't wait till the last minute. Try to keep track, watch the news, all you really, the Weather Channel app will even tell you, when something happened. Don't just pay attention, you'll be fine. By all means, do not go to this site, and I list the site at the end of the semester, and try to catch up on all the earthquakes that you missed, because it's impossible. Well, sure enough, every year, somebody goes to that, and then I get this email. I'm just trying to catch up on things, and I went to that site you gave us, and oh my God, there's like 12 earthquakes a day. Do you really want all those on the map? No. All right, and this is what I was getting to. I told at the very beginning of the semester, I say you put stuff that makes the news on there. Affects people, affects civilization. There are so many earthquakes that we just, the machines catch them. They're paying attention. All right, but the news cycle, you know how that is. So they're not going to report on these things out in the middle of nowhere. Now, unfortunately, as we said, over in the Pacific, a lot of those do run through some islands. And, you know, when an earthquake happens, there is something called a tsunami. It's that giant wave, right? That can be a problem. That does make the news. But, you know, something happens in the middle of the Pacific, you don't hear about it. Two words that I really struggled with as a student. I have no idea why I found these so difficult. I'm not saying they're hard or they're not hard or whatever, but boy, I just never got these down as a geology student. The focus and the epicenter. All right, and they use both of these. Even in a newspaper article or a news article, usually you'll hear epicenter because epicenter is going to be the name of the town. Okay, that's the location above the focus. I know I didn't tell you what the focus was, but that's at the surface of the earth. Watertown, New York received, da-da-da-da. The focus is where the earthquake actually is. And they'll go on later in the article and say something like, the earthquake was 1.3 miles below the surface. That's the focus. So you can maybe think of it as, focusing in a camera on that point. That point is where the seismic energy release, that point is where the earthquake is. The epicenter is the place they name. That's a name you're going to know. So again, a couple more test questions you really just, you don't want to miss because they can be really straightforward and simple. I think I have a little graphic. I do have a graphic. So we have our fault there, the break in the rock. It slips, releases that energy, radiates out in all directions, but one of those directions is going to be received. It's going to be felt, it's going to be noticed. That's typically what we call the epicenter. Now, there's other areas. All right. The earthquake in Albany, we felt it here. I believe it was an Albany one when I got talked to up in Rome. That would not be the epicenter, but it would be somewhere that felt it, completely different. They don't have a name for that. As you can imagine, just like a bonfire, it's most intense directly at it. And as you move outwards from it, it does recede with distance, right? Just like thunder. There's a lot of parallels between sound waves and earthquake waves. That's why a lot of times when I talk about it, I do, in fact, clap my hands for that. I know you guys can't see sound waves, but you get the idea. And in these rooms, you could kind of almost hear them echo, travel a little bit. I don't know how well that transfers on the computer, but okay. In this part of the book, they go into a little more detail than I do. Try to keep it, to the level that I do. But by all means, please, read, and if you have questions, ask. But when it comes to being, concerned with regards to test questions, don't try to get too much more involved than we do conversationally here in the next couple minutes. So, as I said, when it happens, the energy is released. Okay? and it travels in waves. Those waves are called seismic waves. And as I said, they're rather similar to sound waves. If you remember being a little kid and last time you played with ropes, maybe you still play with ropes, but whether it be a jump rope from your little cousin or whatever, you're misusing it. Kids like to play crack the whip. Indiana Jones wasn't so big when you guys were kids. You knew who he was, but when I was a kid, man, it was, So we're trying to do whip things. It's the same idea as you crack that whip. The whip goes up and down. You'll see some waveforms in a little bit. All right? And then that sound that's released at the end is also a function of that energy that's traveling through that whip. There's no more rope. The energy's released. So anywho, we look at P waves, S waves, and I say Raleigh waves. It's probably Rayleigh, the way it's spelled, but I don't know. I always say Raleigh. I try. But, so, Raleigh waves. We don't have pronunciation tests, luckily. So within P waves, S waves, and Raleigh waves, see, I did it already, we've got two bigger categories, all right? And they are surface waves and body waves. Body waves are the two of these, the P waves and the S waves, and that is traveling through the earth. That's the body, okay? So the earthquake happens, the waves travel through the earth. Those are body waves. When it runs out of earth, just like that whip runs out of rope, it hits the surface. At that point, they call them Rayleigh waves. Rayleigh waves. So that's what we mean by body and surface. Surface waves are just a combination of the two body waves that can be released. So what's up with the P and the S? Well, again, for once, P and S stand for something simple. P is primary. I'm not going to jump slides on you here. S is secondary. So the energy from the P wave is the first wave of energy that arrives on... Can you guys all picture, again, you've seen it, seismograph might sound familiar, but what we're talking about, again, you've seen it in TV shows and movies. It's that little strip of paper with the red pen that's bouncing up and down on it. Kind of looks like EKG, but it's for the earth, okay? And, when the earthquake hits, it starts shaking. You'll see it in monster movies when a giant monster, Godzilla, if you watch Godzilla movies, okay? It's just a measure of the trembling, okay, that's going on. So that hits the seismographs in two waves. The first wave, the primary, and the second wave, the secondary. Now, we learned a little bit about this in the last 100 years. Again, we started learning, unfortunately, as we were blowing up nuclear bombs, atomic bombs, we realized that things were shaking the whole damn earth. Okay, very powerful stuff. And when we knew that one was scheduled, well, we could pay attention to our little machines a little more and try and get some useful data out of it. So we learned that P waves can travel through solids and liquids. You'll see S waves are a little different. They're compressional. What does that mean? I'll show you. It means that energy travels parallel to the wave direction. But again, that's probably, I don't want to say meaningless at this point, but not exactly crystal clear. When we show you the examples of the waveforms, you can go back and put them next to your notes in here. You can draw the little waveform, and it'll make more sense that way instead of having it afterwards. The S wave, as we said, is secondary. It travels slower than a P wave. And it only goes through solids. S, solid. Another thing I somehow did not pick up on when I was in college, and I don't know, which one goes through what? I can't remember. S, solid. All right? So in other words, the S waves get absorbed when they go through anything that is not solid rock, i.e. molten rock and or water for that matter. And now with S waves, the energy travels perpendicular to the wave direction. You may recall now this word makes a little more sense. You remember that perpendicular talks about at a right angle to straight line, right? But still, it's much better to see it than to hear it. You see, isn't that better? Not 100%. So, the S wave is what we've been talking about. That is you snapping the rope and it going up and down, up and down, up and down. Okay? Which way is the energy moving? The energy is moving forwards in front of you. But think about it, it's traveling through the whip up and down. You may argue that it's not exactly at a right angle. I dig what you're saying. I get it. All right. But if you were to draw a straight line through here, and you drew a perpendicular to the center of each of these waveforms, you'd get your 90 degrees. We don't get into math too much in here, but that's what they're talking about, okay? Up, down, up, down, up, down. 90 degrees either way. And the energy travels that way. If you've ever stared at the ocean, same idea. All right. The P wave, you've more than likely illustrated while fidgeting with a slinky. We all do horrible, horrible things with slinkies that they aren't meant to do. Slinky had an average lifespan of a day and a half to maybe 3 in my house. It would always end up tangled beyond all repair. In all honesty, they really didn't do the stair climbing thing like they did back when I was a kid. Stair descending. They don't climb stairs, but stair descending. I don't know if they started making the plastic ones. Totally not. But they just, so the kids would screw around with them. And I'm sure we ruined our share of them as well. But this one, and I think I have a video of it here. We'll see. Hopefully it'll twerk. Not twerk. Work. Takes Safari a minute to kick in usually. Nope, it's not even bouncing, so it did not register. I'm sure nowadays there's much better ways to put. Oh, it did open, just didn't open. No thanks. I thought this linked to the actual Slinky. So the S wave's up top in this one. Really? All right, YouTube generation. Where's the loop button at? This is way too short. Is it under settings? I'm a Mac. Hold on. I do have right click. I just can never remember if it's function or command. Stop playing. Loop. All right, so, and hopefully the recorder's catching this. So again, at the top we've got the S wave going through, and you see that. Imagine cracking your little rope there. But the longitudinal wave at the bottom. So take that slinky you got and sit at a table or a counter and stretch it out about arm's length from one to another. And with one of your hands, doesn't matter which one, give it a sharp little rap, a sharp little shake. Again, you're sitting on the counter, it's not in the air. All right. And what you'll see is this tightening through the springs as it moves from whichever way you whacked it to the other. Okay? And the energy's traveling through there is compressing those strings there. Springs. And that's how it moves through. So we have a left to right, for lack of a better word, movement. And we have this up and down movement. That's important because of what's coming next. Again, if this video did not come through to you folks at home, I do apologize. Please click on the link and Watch it. Because I'm sure it was super informative for these guys. So we want to understand that motion because when we get to the surface waves, when the Rayleigh waves are released, and yes, mind you, there is a lag. We implied that by saying primary and secondary. One hits before the other, but at some point, they're both being emitted. They're both being released at the surface. It's a combination of those two energies. So this is where, stuff gets destroyed. You've got two directions, so to speak. Remember I said, just left to right. Left to right is arbitrary, but left to right shaking from the one wave. You've got the up and down shaking from the other, and that just grabs a hold of stuff and, bridges, buildings, think about that kind of stuff that's usually destroyed. First of all, the waves end up traveling slower because, again, you're muddling two things together. But it still keeps on moving. And this is what causes the damage. I guess side to side and up and down is better than left and right, but same idea. So this isn't really super informative, but I felt obliged to show you a waveform for the Rayleigh waves. So you have the forwards and the up and down motion going on in it. We saw the word ground roll in a previous, on the last slide at the very bottom there. This is what's sort of going on here. And it is can be thought of as a ripple going through, but more so it's that constant barraging of the waves that just keeps stuff shaking. And again, the energy slows down, which certainly doesn't help things. You're just going to shake longer. All right. So there are two ways that we have looked at earthquake energy, earthquake damage potential over the years. The Richter scale and the Mercalli scale. You are familiar with Richter. It's a 4.3, a 2.9, a 9.8, God forbid, whatever. Okay, it's that number. It's numeric. And this is what the seismographs give us. That is the point of those little pen marks on the sheet of paper, and I really hope I have a seismograph reading in here. I should. If I don't by now, I really need to add one. I think we got one coming up. If your seismograph is kept, well maintenance, you're going to get the same reading from the same waves no matter where you are. Okay? In other words, we get comparable data. And scientists like that. It's quantitative, quantity, numeric. It's objective. Machines don't lie. They can be incorrect if they're not tuned properly, if they're not calibrated, so on and so forth. But it is what it is. You stick a thermometer in your mouth, you get a number. And that's nice, as I said, because then they can compare stuff. Compare and contrast. Okay, we had a 9.8. I gotta quit saying 9.8. That's just like town ending horrific. We'll go down to like 4.7 or something like that, okay? Strong, but things are still standing, so on and so forth. So you got a 4.7 in downtown LA. You got a 4.7
in a village in the middle of South America, Russia, wherever, somewhere. We're going to have a village in the middle of not as high tech is my implication. Anywhere. Middle of Iowa. I don't know. So, what happened? What's the result? Did it behave differently? Is there different rock types here? Are there different structures? Usually it boils down to different structures. We're working on building earthquake-proof. We're not there yet. We're working on it. But because we know that that bottom line number is the same, we can work from that. It's comparable. This is the equivalent of when we talked about why it was so important to date meteorites, so we can find out, hey, okay, everything on the solar system is roughly the same date, the same age. We can look, at all the different things, see how they've changed differently, but we know one thing is constant. Same idea here. On the other hand, we've got Mercalli scale. Mercalli scale measures intensity. How bad was it? Well, it's so bad that ... It's qualitative. It's descriptive. Now, I'm going to blame most of the problems here on people. People like to talk. If they either don't get in front of the camera because they don't want to, or if they're in front of the camera, they want to talk. And some people like to tell stories. Some people maybe don't want to appear afraid. Some people have no problem appearing afraid. It's subjective. And in science, and that's one of the things we talk way back when we go back to the nature of science, and we some subtle slight jabs at sociology and psychology that sometimes they get called the softer sciences and so on and so forth. It's because it's dependent on people. It's not about the science itself, it's about the subject matter. People are really hard to gauge and compare. So, it's not just the people. That doesn't help. So let's go back to that earthquake in Rome. Not in Rome. It was in Albany, but we felt it in Rome. So I'm in my lab room, and 2 doors down is the lab manager's office. Outside her office is all of the equipment for the chem labs. So she's got hundreds and hundreds, if not thousands, of beakers and Erlenmeyer flasks and graduated cylinders and thises and thatses and whatevers. All those stuff you've seen. And we're down in my lab with my rocks and whatever else. They held other labs in there too, but you get the idea. So we're sitting there, and I don't want to say we didn't even notice it, but anyone who did notice it probably thought a big old truck rumbled by, hit a speed bump outside, and boom, 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 boom. Well, her whole freaking room rattled like wind chimes. She came running down and said, "Oh my God, you guys all right? Did you hear that?" We're like, "What are you talking about?" We didn't, no, we're fine. No, we didn't hear a thing. What did it? What's going on? So, 100 feet away, completely different experience. You go back to interviewing Joe Random on the street. Somebody might have a china cabinet full of crap that shook like crazy. Little old lady had plates on the wall. They fell off. Somebody else in a much more different apartment style. Nothing. Their cat ran and hid. So, we didn't always have the ability for Richtering things. All right? Pardon my conjugation. Mercalli's been around forever. They tried to quantify Mercalli. It's a pretty good job. I know you can't read this. I'll tell you some of them. It's now called the modified Mercalli scale. Lowest level, only felt by sensitive instruments. Then felt by few persons at rest, especially on upper floors. Yeah, that can matter. Delicate suspended objects may swing. Felt indoors, but may not be recognized as an earthquake. Vibrations like large passing truck. Oh, sounds familiar with what I just said. Felt indoors by many. Some outdoors may feel it. may awaken some sleeping persons. You see where this is going? So it's really, they're trying to quantify it with measurable things, but there's just and there's absolutely nothing wrong with those descriptors, okay? But they're just not very sciencey. And as I said, they do try and attach it to a Richter magnitude. With 3.5s, we tend to see, let's go across here, felt indoors by many, some outdoors may awaken some sleeping persons, dishes, windows, doors may move, cars rock, and all of the things before that. Not only that, but you get these. So they do that, but it's variable. As I said, we've started now, engineering's coming along, especially in China, in Japan, where not only do they have a reason, but they've got the tech, okay? In LA, we've got reason, and San Francisco, we've got reason, and we've got some tech. They're working on this stuff. They build these buildings on springs, giant coils in the basements and where the parking garages are. So these things aren't rigid and they just don't snap. Crazy idea, but seems to work. Where again, you go back to the village, the generic village I was talking about, and those structures, they may just crumble like a house of cards. Or you get the Three Little Pigs scenario where you got straw, you got wood, and you got brick. Some things level, some things don't. It's all over the place. So Mercalli's nice. People understand it. But in science, they like the Richter scale. So it's actually based on the height, the amplitude, if you would, of the... Let me skip ahead here real quick, see if I do have... How do I not have... Damn it all, I'm going to grab one. I can't believe there's not a picture of one in here, because I keep updating this, too. Take 5 seconds. Just like a telegram. Kids all know what telegrams are these days. Just like a telegram, a seismogram. There we go. Right off of Wiki Commons here. Let's grab that. We should probably grab the citation too. Always cite your work, guys. For the moment, I'll just make a new slide. I'll figure out how to add them in fancily later. I said I'll do fancy later. Where'd the text box go? There's that text box. Where's the other one? Insert text box. So there's that, and then let's get a close-up of a seismogram itself. Just keep it simple. Shutterstock. Shutterstock is usually open source or whatever, right, you guys? What is it by person? Oh, it's not an EKG. No, I think I thought it was an EKG. All right, now I don't even have to cite it because it is there. So, Richter scale. All right, let's make this big again. Richter scale, we're measuring the amplitude or height on a seismograph, on a seismogram, which is made by a seismogram. And this logarithmic increase, that'll come in a moment here. When we jump from one number on the Richter to the next, a 4 to a 5 to a 6, it's not like when you move from an 83 to an 84 on a test. It's more like when you move from an 80 to a 90. All right? That's what they mean by logarithmic. It's a bigger jump. So, here. Each jump is a 10 times increase in magnitude, all right, and a 30 times release in energy as we go from a 4 to a 5 or a 5 to a 6. So energy release is 30 times worse. Magnitude, the height, okay. That's not quite how to explain magnitude, but all right, let's look at the thing. So this is that machine that we talked about. There's a little pen here. You unfortunately can't see it. Nowadays, I'd like to think they're digital in some way, shape, or form. We're not just going through all these rolls of paper. But, you know, for many, 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 many decades, it was just roll after roll of paper. And there's a little pen. Can't believe I didn't grab one that you can see the little pen on. And it literally just drags across this drum as it rolls. And when something shakes, the earth shakes, the pen shakes. The bigger the event, the bigger the pen shake, to the point of, you know, this is background nothing. Oh my, something's starting to happen. And then, yeah, there's the trembler. And it comes back down. Then it hits again. So this is literally a physical recording of what's going on. I mentioned some 9-somethings and then promptly said, oh, I should stop talking about those. They're horrific. They are. Thank goodness we have very few of them. Think about it. If earthquakes are energy being released and we're measuring how much energy is being released, essentially, that means that it has to build up for a very long time, or something really needs to change. All of a sudden, plate tectonics, you know, increases in an area for some unknown reason. But generally speaking, we think of it as a function of time. And that's why you'll hear them say a lot of times they'd rather have several small earthquakes because it lets off the steam, so to speak, right? Lets out that energy. It doesn't let it build up as much. You've heard me talk about the Christmas tsunami. 2004, so it was a couple years after I started here. And like I said, those islands, there's some parts above sea level, but everybody lives down by the shore because that's where, you know, sustenance, transportation, that's where everything is. It was, I don't know, thousands of people died. It was rough. 1964 in Alaska, they still talk about that one. Liquefaction happened. Liquefaction is certain soils will basically turn into like ball bearings, BBs, and neighborhoods. This was a coastal area, and neighborhoods kind of just rolled off of a cliff, and it was messed up. I don't know much about the Chile one, but 9s are bad. 9s are really bad. I'm not sure what the Cuba one was in recent memory. It was bad. I think it was just in the 7s, though. I don't think Cuba had a 9-something. was in Trump's first presidency. I think that's the one they were teasing him about throwing paper towel to people or something. It was not kind of people to tease him about that, but it was an odd thing. I'm not sure what was going on, but that's the memory bite I have of it. But I want to say that was a 7 something. I'm not going to go back to the internet and Google it again, but it was bad. But again, you're looking at the structures that they have there, how close to sea level they are, a handful of things. Not that a 7 in LA wouldn't be devastating, but it's still a different kind of devastation. So we're kind of talking about this. So what does vary it? What does make an earthquake allow it to build up or happen more frequently? A lot of it is dependent not just on the plates moving, but the type of rock. All right. We talked about rocks in the beginning because they do, kind of run as a common theme throughout this class. What do you think? Putting pressure on you guys, don't have a whole lot of people here today, but what do you think is going to be able to hold up or store more energy? Some sedimentary rock or a piece of granite, for example? It's a piece of sandstone or a piece of granite. You're going to try and break it. What should break easier? What's more durable? Yeah. Okay. And I know we talked about how at the very base, the core, ocean floor and continents are igneous rock to begin with, but you've got all of the sediment on top of it, and oftentimes that's what's holding it up. Sometimes it's not, though. So we can talk about, this fault is mostly held together with sandstone and shales, and that's going to slip a lot easier than something that's locked up with, say granite against granite and so on and so forth. I'm giving you sort of educational examples that might be a little harder to replicate in the world, but trying to get the idea across to you. So some of these faults can hold a lot longer, and again, that's supposed to be a bad thing in this instance. Now, there's a video that I try to show. Usually it happens near the end of the semester. I might just assign it as a out-of-class assignment. We'll see how many days we have to work with here. San Francisco earthquake, 1901, 1903. Can't remember exactly when it is. It was a mess. It was a mess. As you can imagine, again, we didn't have the engineering technology back then. They were no strangers to earthquakes, so they did their best. But what hurt San Francisco way more than the earthquake was the after effects. It burned, and it burned, and it burned. When you've got, well, I won't phrase it that way. Let's just say you've got your water pipes and your gas pipes in the ground, right? So when your gas pipes break, you're going to have problems. Should that cause fires, your water pipes more than likely broke as well. You can't put them out. So we see a lot of secondary fire damage, just like when we watched the St. Helens video, right? There was the volcano itself, and that caused some damage, but then there was the flooding, the mudslides, all these secondary things. So we see a lot of secondary. It's not just the earth shakes and the building falls. It's then what happens. So that we have to worry about. So I mentioned tsunami a couple times, not just today, but throughout the semester. Fairly, I don't want to say famous word, but it's out there. They've pretty much in the media stopped calling these tidal waves, but that's really been in the last couple decades. So, since I've been teaching. It has absolutely nothing to do with tides. It happens in the tidal zone. That's where we see it. But it has nothing to do with the tides. It's much more akin to a hot tub or jacuzzi. You've got the air pushing out into the water, and it sends these little bubbles to the surface. They bubble up like a nice little cauldron, right? Well, again, we don't have a constant, hopefully, release of that energy. You've got, oh, that was a bad clap, but you get one poof release, and that sends a bulge through. Now, there's all these reports, many, many reports of these ships out there that barely even noticed the waves at sea from a tsunami. The thing about waves is that they need to hit the ocean floor in order to start sort of collapsing in on themselves, that waveform to break down. And then it starts piling and stacking on one another, and then it gets really big. Out at the ocean, they might have just been like, wow, that was a big swell, big roll, especially the bigger boats. Now, of course, sure, you could get massive waves out at sea, not saying that you can't, so on and so forth. But a lot of these, you don't really notice the effects until you're at the coasts. And what happens is, if you've been to the ocean, you're familiar with how the tide goes out, the tide goes in, right? The wave, not even the tides, but just the waves. And you feel that pull. If you've been in the water, you know the pull I'm talking about. Well, when the tsunami finally gets to shore, that pull, well, no, before it gets to shore, that pull just keeps happening because the waveform is building and building and building, and it's pulling out all the water that's there. Oftentimes, hundreds and hundreds of feet are cleared out of what would be, beach, way more than the tide. And then, once the rest of it catches up, it just keeps rolling in and rolling in and rolling in. And it goes way up, past the stairs, past the parking lot, into the condos, into the towns. It just keeps coming. And while this has probably been happening for, century or so, however long we've been large-scale inhabiting beaches that we probably shouldn't be building structures on, and going back for thousands of years, of course, when we just had villages along the shorelines, we now have cameras everywhere. So, and I wish I had saved this video, but it's on one of these, beachfront condos that's there, and it shows, or it could have been somebody standing in their balcony, I don't even remember, but it shows that water going out. And the curious little monkeys that we are, we walked out. I know the Japos probably would have been wandering there. Now that I know why it's doing it, I would probably make us get the hell out of there. But you never know. Everyone's like, where's the water going? I don't know. Let's go see. Where's the water going? That's what we do. And then it came back. And most of the people figured out quick enough to run like hell. But you could still see there were people who were either, sleeping on the beach, drunk on the beach, whatever, that it comes up, they're well above the tide line, at least last time they checked, and the water just comes whooshing up, and they're flipping out over their chairs, and it keeps coming, and it keeps coming, and it keeps coming, just like I was explaining a couple minutes ago. So we've got this stuff on video now, and again, talk about updating my PowerPoint. I should try and find one of those, because it's unbelievable. We also get these when asteroids or meteorites hit the Earth. There's all the talk about the one with the dinosaurs, right? The Chicxulub crater in the Gulf of Mexico. It's a big impact crater. They blame it on the demise of the dinosaurs. Again, in reality, it was probably just sort of the last nail in the coffin scenario, but it sure as hell didn't help. Back to the point. So you're familiar with the Gulf of Mexico, right? We've got Central America, you got Texas, you got Louisiana, Gulf Coast states, you got Florida. They have flood deposits. Flood deposits in the Dakotas from it. So, whoosh. Now, mind you, things were a little different. Sea level was a little different then, so on and so forth. But holy cow, Louisiana up to the Dakotas, that's a lot of water. Those are tsunami deposits. Okay, I said flood, but there's the ash everywhere from that impact. They can date it to the right. It is huge, huge. All right, enough about tsunamis. Really cool, but incredibly horrific things. Basically, we can't do it. We got our best people working on it, believe you me. There are foreshocks. Foreshocks happen. You know what aftershocks are, right? Those are little tremors that come after the earthquakes. You hear about those all the time. Well, there's foreshots as well. Not to get gross, but let's think back to maybe one day when your stomach was really rumbling and grumbling at you, and you're like, oh, I better go to the bathroom. Think of that as a foreshock. We get those. But just like the bathroom scenario, it doesn't always lead to an event. That is pretty much, at the moment, one of the best tools we have, though. The problem is, again, think back to these areas that we want to be concerned with. Beijing, LA, whatever huge, large populated area that is right on a damn earthquake center. As a planner, as a mayor, as a governor, every time you have foreshocks, can you evacuate your city? And let's say that you do decide to, and one time goes by, everybody somehow manages to get out of LA in, an hour, or who knows how long you'll have. But let's say you get a decent amount of people out in an hour, and then nothing happens. How likely are they going to listen to you a second time or a third time? You turn into the whole Chicken Little scenario. But it's a double-edged sword. They sued, and I think very effectively sued. It was a while back, a decade or so, in Italy somewhere, that the geologists did not properly warn them in time of the earthquake. And they got some compensation from somebody somewhere. Certainly not the geologists. They're usually quite poor. But, we don't have a tool. Satellite imagery, maybe. Again, if we're constantly monitoring it and somebody writes some great software, you might see, subtle bulges in the land. But again, that happens all the time and doesn't necessarily mean it's going to break in half. The best thing we do have is animal behavior. But again, it's not enough time to clear out a city. That scenario I was talking about where all the silly humans wandered out into the ocean and then it came up and flooded and flooded and flooded. Not a single animal was lost in that event because they all ran. The critters, and whether you want to blame it on the soles of our shoes, the concrete under our feet, or whatever, it's not like they're more special than us. They don't have a sixth sense or anything like that. Okay, they're just a little bit more still in tune with nature than we are. And they pick up on these subtle changes and react with, a reaction. Not a rationalization or a ponderance or anything like that. Run first, ask questions later. That's what most critters operate on. That's really the only reliable thing we have, but you can't, again, run city planning on that. If you get one thing out of this whole lecture, or even hell, this entire class, it's that if you're walking down a path towards the woods,
and what looks to be every single animal that would have lived in that woods is running out of the woods, don't go into those woods. There's probably a reason they're leaving. All right? Trust the critters. But again, that's certainly not enough to save a town. Now, fighting an earthquake, we're really good at that. Really good at that. I got a couple minutes. I got to wrap up. So I do have my pictures. They're just way down here. We're going to do this in lab. It's kind of cool. It's an online exercise, actually, which is even cooler for you guys because you have to go to find a computer and do it. So we'll be really sort of short in the lab room. But it's called triangulation. It's the way cell phone towers work nowadays, the way they find lost hikers or escaped criminals, excuse me. Use 3 points to find a fourth. Okay? So the thing is seismographs record distance, not direction. Within 50 miles of here, there was a 5.6 earthquake. Well, okay, you could draw a circle around that seismograph. But oftentimes we want something a little more specific. Yes, nowadays with the media, social media, we're so connected now, you're going to know within minutes where it is anyhow. But again, think back 10 years, 15 years, when news didn't travel quite as fast and so on and so forth. So you'll see it here in a second. So there's a way of interpreting these. You're going to do it in lab. And you'll be measuring the height of the tallest one of these. Okay. You'll be looking down here. It's funny, I grabbed the exact same images however many years later. There's usually a time stamp down here, so you look and see the time difference between when it hits here, when it hits here. There's some tables that you look at. You'll get a distance very, very quickly. Again, the height of these gives you the amplitude. I'm sorry, the amplitude, the height is the amplitude, will tell you how strong it was. You use a cool little thing like this. And again, you've got these 50 miles from here, 100 miles from here. This one's probably more like a 300-mile circle. But and the point is that they should all intersect in one place. And where those three circles intersect is where the earthquake happened. And again, that's what they use, for cell phones and whatnot. It's called triangulation. Before they fixed, and this is even going back to the 90s, which I know is forever ago for you guys, but wasn't that freaking long ago, trust me. They had a variance, a fudge factor built into GPSs, okay? Just the average GPS you could go and buy for hunting or hiking. That's why they weren't in cars and so on and so forth back then. They had a signal variance in there. The military had a descrambler, okay, but the average person did not. We had to triangulate, find a couple different points. It was off, I forget what it was off, 10 feet, 15 feet. And they were worried about someone strapping one onto the front of a missile or something, who knows. But they felt the need to scramble the data. And we would have to, I still remember doing a lab in grad school. There was an algorithm you use and a formula, and you'd get a pretty good idea of where it was. You guys, no, we didn't do it this semester because it's spring semester. We usually do it, and we do it at the end of spring, and we do it at the beginning of fall. And the joke therein was that they still kind of suck. So we'll talk about that in a few weeks. Well, hopefully we'll get some nice weather and actually go outside. But arguably, any GPS that you're going to have in your hand, unless you've got one of those multi-$1,000 units that like the water company uses because they need to know exact depths and so on and so forth, you've got a 10-foot fuzzy circle around you still. But that's more because we don't want to pay for good technology. You're trying to go to Starbucks, you're going to see the Starbucks sign well before you
need to know the exact driveway. And we've probably all encountered that with our GPSs in our cars and on our phones. It wants me to turn here, but the road's over there. And then the silly people that drive into lakes because they listen to their things and don't actually look. So they're not much better nowadays, but at least it's not purposely scrambled nowadays. Okay, we don't really need to focus on this too much. You know, you've heard me talk about the earthquakes around here. I think this was the one that we felt in Rome. Talked about aftershocks. Typically, aftershocks are smaller. Sometimes they're bigger, though. Makes you wonder then if they need to call the original one the foreshock then. Oh, and then this goes back. You can't really see very well. Let me see if I can enlarge this. Should be bigger by now. Oh, this is before I was doing. This should just be in a pasted in image. Nope, you can't see real well. Just in the peninsula here coming off of Alaska, there's probably a dozen yellow dots all along California. And north of California here, there's dozens and dozens. And this was all from 1 week in August. This goes back to my, there's so many earthquakes that go unreported. They're small enough not to be, to cause any trouble. They're in the middle of nowhere. Nobody cares. But the U.S. Geological Survey, always looking, always caring. All right, so that's it for our class discussion of earthquakes. Like I said, your textbook might go into some other stuff. And it's neat stuff. Feel free to read about it, be interested in it. If you have questions about it, do please ask. Hopefully I'll get to show you the 1906, now I'm saying 1906 in my head, the 1906 earthquake in San Francisco video. It was recorded in the 80s. And the cool thing about it, in a PBS-y sort of way, all right, so relatively cool. But the cool thing about this is that there were still people alive then who were in that earthquake, and they found them and interviewed them, and it made it a lot more interesting than just, some guy talking to you. Who's the guy that does all the documentaries now? Morgan Freeman or whatever, just I won't even attempt to do a Morgan Freeman voice. But at any rate, they've got real stories in there. And I've got another one about building the Hoover Dam, which, again, I've seen it without the interviews. It's really dry. But to hear these old guys talk about it, and then they were, a loaf of bread was 5 cents, and they gave us 7 cents a week, and we could do that. It's more entertaining than it would have been otherwise, at any rate. So I don't know if we'll get a chance when we get to water to watch the Hoover video, but I will do my darndest to show you the San Francisco earthquake video. It's pretty neat stuff. So that being said, farewell.